Okay, friends, we're going to continue on with logs. So this is our last chapter this year, and here we go. Okay, so we have just looked at we just looked at finance, water, and half-life. Now we're going to look at half-life, earthquakes, and natural logs, an introduction to natural logs, which we'll study further in calculus. Take a look at some great pages to look at and some more go formative questions to consider and to complete. So here we go. So we're going to look at exponential growth. We're going to look at earthquakes, and we're going to look at population growth. I'm going to forego on this video. You can watch that on your own time, and you can watch this interesting video clip as well, but it has to do with bacteria growing on your cell phone, and it does grow exponentially. So I'll let you watch that on your own time. This is also an interesting video, which we'll also look at in class. But here's where we are going to start. So we'll take a look at earthquakes as well later on in this lesson, but I won't be going over this demo inside of this video. That'll be for in-class time. So you can look at this video or this information on your own time. Alrighty. Okay, so let me give you a quick intro to earthquakes. A few years ago in Victoria, we had a 3.3, and about 20 couple years ago, there was a huge earthquake in Taiwan, and we slept like babies in Victoria, and yet the 7.7 wreaked havoc in that part of the world, and many people were killed, injured, and buildings destroyed. Incredible costs, both to human lives and to the buildings around. So why the difference between a 3.3 and a 7.7? Well, it has to do with the Richter scale rating and what the Richter scale rating means. So let's take a look. So you can see that a Richter scale rating of between 3 to 9, which is what between 3 and 4, is basically just a big truck driving by, whereas a 7.0 or larger has buildings being displaced, cracks and underground pipes broken. So you can see that in terms of the definition there, it's bigger. But why so much bigger? And here's why. Richter scale rating has a base of 10, or there's a 10-fold difference. So a Richter scale rating of 2 is 10 times more than a 1, and a 3 is 10 times more than a 2, which means a 3 is 100 times more than a 1. So if we were to compare a Richter scale rating of 8 to 3, that's a huge difference. You can see it's 100,000 times difference, and the reason for that is it's a 10 to the power of 8 versus a 10 to the power of 3, and then at the end of the day, it's a 100,000-fold difference. So that's a warm up for you. So you'll be prepared to do the earthquake questions later. Okay, so now let's take a look at this question. As always, pause the video, try it on your own first, and then give it a go. All right, bacteria living in your mouth multiply 5-fold every 20 hours. This statistic is not true. This statistic is for the sake of the question, not for the sake of your dental hygiene. So here's how we might consider it. We're going to compare the initial population to the population after we increase it every 20 hours by 5, and I'm simply going to put in 8 for time and compute. And when I do that, it's roughly a 2-fold difference. Okay, again, pause the video and give this a go. All right, a community of rabbits living near the university multiplies 5-fold every 20 years. How long would it take for the population to double? And we've done this type of question numerous times. And so what we're going to do here is we'll have our initial population. We're going to double that initial population, and then we're going to use the 5-fold change, the half-life, well, not the half-life, the 5-fold life. A half-life, if that rate was 1/2, then this would be the half-life. Since it's a 5, this is called the 5-fold life, and we're just going to isolate for I. So, of course, all we're going to do is solve for t. So we divide both sides by I. We take the log of both sides. We'd use the power rule to bring down the exponent and solve. So now what we're going to do is have you solve this question. So how many times more intense was the Taiwan earthquake compared to the Victoria earthquake? Pause the video and give it a try. All right, so there's the solution, and here is the help. So essentially what we're doing is we're comparing the 7.7 to a 3.3, and all we're going to do is divide those, because if we said how many times greater is 20 than 4, we'd simply go 20 divided by 4, which would be 5. In this case, we're saying how much greater is a 10 to the 7.7 versus a 10 to the 3.3. We're going to divide those, and that's how it works. All right, this one's a bit more challenging, so I ask you to pause the video and give it a try. If the Victoria earthquake is 3.3 was 3 times as intense, or 3 times more intense, what would we have noticed? What would the Richter scale rating be? So there's lots of ways of thinking about it. I'm going to share with you one way. So the answer is we wouldn't have noticed much, because increasing it 3 times does not do much, and we'll show you why. Okay, so you might be tempted to think it would be a massive difference, but at the end of the day, it's not that much, and we'll show you. So here's the Richter scale rating of 3.3 would mean that we have a base of 10 to the 3.3. Now, if we multiply that by 3, we've clearly tripled it. And another way of saying that is, remember with exponents, if we're multiplying it by something, we're going to be adding that r. Well, remember that r, because of our exponent laws, would be multiplying this by 10 to the power r. So what we're really asking is 3 to what power of 10 makes this true. So we're basically going to set 10 to the r equal to 3. We'll take the log of both sides and isolate for r. So we take the log of both sides and isolate for r, which gives us that rating right there. So 4.77. I have too many zeros there. That should be 0.477, not point. Okay, so then when we add that together, the 3 plus the 0.477 gives us this, and we can see it's still in a very light rating. Alrighty. So now what we're going to do is we're going to take a little break just to introduce you to a new number. It's called E. Press that button. When you press that button on your calculator, you're going to get 2.7182818828, and you might wonder where it comes from and also why it's important. For now, before I show you its importance and its context, which might be a strange way to do it, we're just going to make sure we know how to use your calculator with it. Okay. So just to know that y equals log base e of x is the same as, this is ln x. When it's written as ln x, the base is e. So earlier we looked at common logarithms. When there's nothing written, we know that's base 10. Otherwise, it's the base stated. But for right here, the base, when it's written as ln x, the base is e. So those two are exactly equivalent. So if we were to convert that, it would be e to the y equals x. Okay, and if you were to convert this thing, I'd ask you to do that right now using what you know of log laws. We know that it simplifies to 5. In equations here, determine the growth rate. So the growth rate is that little guy there. So the growth rate here would be 5%. And this is, in this equation here, when we have a base e here, the growth rate here would also be 5%. And they have a slightly different value if you calculate these, but for now we're just going to go ahead and say that their growth rate for both of these is 5. If you were in class, you might be ahead in the lesson, so I get you to try these questions, but for now I'm going to go on and say basically who cares about base e. So what I'm going to do is click on the who cares and do a couple things. So questions: when will we run out of clean drinking water? Because we know our population is growing. When will we run out of oil? When will we run out of space on this planet? These are all questions that global planners and politicians and people who care about the planet are asking. So when will we run out? And we can model population growth with certain formulas, which we're going to look at. So one thing I'll get us to look at is just this interesting graphic here. And I encourage you to look at this on your own time, but this is just the world's population, and you can see that it's growing. You can see the largest countries in the world and how they are growing. We'll wait for a new birth. Where do you think I think it's going to happen? Oh, India is trying to catch up to China. So anyhow, this is a really interesting thing. This is the world's population, and there's the year 0. or 2,000 years ago, roughly. And you can see that for about the for the first while, things were moving in a linear fashion. It's pretty easy to plan for that. Okay, but then at around 600, our population took off, and it also was linear for a while. Again, fairly easy to plan for. But then things started really speeding up. As you can see, there's the Dark Ages, there's the plague. You can see a dip in the population there. But at a certain point, now we're into this sort of exponential growth, and you can see it's a very different curve, isn't it? So we can just see that it's just shooting up, and it's just, moving fast. Okay, so you notice that it's projected to sort of slow down here, but this of course is just a projection, and what needs to happen for that to occur. So something to think about. And so basically what we're going to be talking about today is growth that is constant or continuous, because world populations grow all the time. That compounding growth doesn't happen once a year or once a month. It happens every single second of every single moment. So what I want to do is show you the E approximation and where this came from. So first off, here's an approximation. I think this is the first bunch of digits of E. So it is an irrational number, and I'm going to show you one way that it was first discovered. Okay, so what I'm going to get you to look at is here is how did I get that? Okay. Okay. All right. So you know this formula. This is our compound interest formula. We're going to start with a population of 1. We're going to start off with an interest rate of with 100% growth, and we're going to do that for 1 year. And so at the end of this time, remember that would be 1, that would be 1. We'd expect that this value would be 2. Okay. Now what we're going to do is we are going to increase the compounding period. So I'm going to increase that compounding period to 2. Do you notice that it changes just slightly? Now I'm going to change it to 12. Now I'm going to change it to 365. So that would be daily interest. Now remember, the E button is 202.718,282. So right now that number there is daily. But what if we increase that to hourly? You see that that's getting closer to this number. Well, now let's make it. This is by the minute, and now let's make it by the second. So this is sort of modeling continuous growth where things are changing all the time. And can you see that number there changed into 2.7182? So here's the question for you. What equation would you prefer to use? Would you prefer to use this ugly sucker? Let's see if I can make that bigger. That's not big enough. Okay. Oh, yeah. Okay, so essentially, as x goes to infinity, this whole business here turns into E. So what that allows us to do is use this formula right here. So we could use this guy, or we could use this whole thing right here. So E to the T R, and R is the rate there. So E being all of this stuff. So can you see all that stuff right there? And R, there's our time. And the R there represents the rate of growth. So that's how that sucker works. And now you know. Okay, so if you'd like to study more about that, you could look into that. But for now, here are your choices. You could either have a compounding period where you put X in for that huge number, or you could use this formula here. So you get to choose. Anyhow, when we get to these problems, let me open this up again. Now, if you were to play with this, you'd be able to do it. Okay, so as soon as when you see the word compounded continuously, we're going to be using our this formula here. Okay, so let's just walk you through that. Okay, so how long would it take for the population to double? Okay, so I just took 7.7 here. I put 15.4 there. because that's doubled. We're using the interest rate of 1.2% as the rate, because this is our continuous growth formula, and there's our t for time, okay, and that time is in years. And you just calculate it, and you take the log of both sides. In this case, I take the ln of both sides, and you know that when you take the ln, that's just going to those will end up canceling out, and that would solve for t. And so there you go. Okay, so hopefully that got you into it. We will look at base E more in calculus, but for now, I hope that this has provided you the support that you need to master this